Good afternoon. Assalamu alaikum. Good afternoon. Hopefully you will give a little bit of your attention to me. And to introduce our today's speaker, I could not have imagined a better speaker and a better speaker than John Ellis and the title. Look, what are we, what do we come from, where do we come from, and where are we going? In particular, if you remember my introduction on Sunday when I made some joke about time and physics, the fourth dimensions and so on, I think that John is going to cover all these. We are very fortunate to have John Ellis coming to our WEP program. John holds the Clerk Maxwell Professorship of Theoretical Physics at King's College in London, but actually he is now posted, as you can see, in Switzerland, in CERN. He obtained his PhD from Cambridge in 1971. He worked at different places, including Caltech, and now, as I said, he's in CERN. And he has been leading the theory division for 6 years. I mean, his work relates essentially to interpret results about the research on new particles. Okay, he's one of the first to study how the Higgs Boson, I think that you will learn a lot about this today, could be produced and discovered. He was currently very active in effort to understand the Higgs particle discovered recently at CERN. Okay, and you learn about the Nobel Prize recently attributed. So, John Ellis, in terms of award, I don't want to cite all of his awards, but I just want to mention the award that he received, the Maxwell Medal and the Paul Dirac Prize by the Institute of Physics. He was elected Fellow of the Royal Society of London and the Institute of Physics, and he's also an honorary Fellow of the King's College Cambridge and King's College London. With such a nice title, please join me and invite John to the stage for his talk. Thank you, John.
So, thank you very much for that kind introduction. Thank you very much for the invitation. Assalamu alaikum. So, the questions that I use in my title taken from this very famous painting by Paul Gauguin. So these people live on a South Sea island, and they probably have a rather different perspective on these fundamental questions from the one that I have, but it's the same set of questions. So they maybe approach these questions from a somewhat metaphysical point of view, and I'm going to approach these questions from the point of view of a physicist with an interest in astrophysics and cosmology. And the take-home message that I would like to give you is that we physicists, in particular we particle physicists, this is our central objective, is to try to at least ask these questions and hopefully find a few answers. And if I want to reduce it down to a single sentence, now, how does the universe work? What is the universe made of? So what do we know about the universe? So we heard something about it this morning in the talk by Priya. Here is a little picture which illustrates you the evolution of the universe over the last 13.8 billion years or so. And during that time, it's been expanding. Currently, the visible part of the universe has a size of about 10 to the 28 centimeters. So 10 to the 28 is rather a large number. So when I'm talking to the general public, I say, well, consider the American budget deficit, express it in cents, and then square that number. And you get something which, at least before Trump came along, was similar to 10 to the 28. So here we have on the right a typical astronomical telescope on a satellite, which looks at stars, it looks at galaxies, it looks back towards the Big Bang. What you see on the far left of the picture, somewhat speckled green and red, that is the earliest radiation that we can see coming from 380,000 years after the Big Bang. So, that's our universe. What is it made of? What happened back then, before the emission of the first radiation? What's going to happen in the future? Is that expansion of the universe going to continue or not? If you look at that picture, it kind of looks like the expansion of the universe is accelerating. But will that actually continue or not? And I'll come back to that question later on. Okay, so as I said, I'm going to address Gauguin's questions from the point of view of a physicist, specifically a particle physicist. So originally, those questions were actually formulated in French. I've already translated them into English. Now I'm going to translate them into the language of particle physics. So what are we? For a physicist, that becomes the question, what is matter made of? And one very important aspect of that question, which I'm going to be emphasizing, is why do things weigh? And that's where the Higgs boson comes in, that was already mentioned in the introduction. If we go back in time, what was the origin of the matter in the universe? We think that that may find its origin in physical processes very soon after the Big Bang. As Priya has already told you this morning, and I'm going to return to that topic later on, astronomers actually tell us that most of the matter in the universe is not made of the same stuff as you and me. It's actually some sort of invisible, weakly interacting dark matter. What is that dark matter? Is that also made of some sort of particle? The time, how does the universe evolve? How did it develop from that very primordial stage until the present? And how did it get to be so big? How did it get to be so old? What is its future? So, those are the Gauguin questions, and our job is to ask these questions and hopefully provide at least some answers. I might mention that when I was a PhD student, I had a copy of that Gauguin painting on the wall in my office just to remind me every day why I came into work. So I don't have the painting anymore, but I still have that same motivation. So as I already mentioned, the Higgs boson, that is related to this fundamental issue of why do things weigh. There's a whole bunch of other questions there, and the answers to those questions, seems to me, are going to require physics beyond what we now know, and that is what we're trying to do now with our experiments, in particular with our experiments at the machine that we call the Large Hadron Collider, the LHC, which I'll describe in a bit more detail later on. And if you have the time, some of you have already done it, you can play with a model of the LHC over in the library building. So this is a ruler with a logarithmic scale, which takes you all the way from the largest scale that we can see in the universe, 10 to the 28 centimeters, all the way back to the smallest scale that we theoretical physicists speculate about, possibly the scale that was relevant right at the beginning of the Big Bang. And in between, we have a bunch of other scales, galaxies, the distance between the Earth and the Sun, the size of atoms, the size of protons inside the atomic nucleus, and so on. And then about halfway along this logarithmic scale, we have the human scale. So Priya showed you this morning several pictures of Albert Einstein. So here's one when he was a little bit younger, together with his kid sister, and they were both about a meter tall. And that meter is more or less on the logarithmic scale, halfway between the largest and the smallest scales that we physicists think about. So what is matter made of? Well, we know that Albert Einstein and his kid sister were made of molecules, which were made of atoms, which had clouds of electrons orbiting nuclei. Those nuclei were made of things called protons and neutrons. And we know that inside those protons and neutrons are more fundamental constituents called quarks. So we particle physicists study electrons, quarks, and related particles. So as I already mentioned, the astronomers, they look out, they see light, particles of light coming to us from distant stars and galaxies. And it's their measurements that tell us that in addition to the visible things in the universe, there must be that dark matter that I'll be returning to later on. So what concretely are we physicists doing? So what we're doing is we're looking inside the proton, inside the atom. We're trying to probe the physics back at the beginning of the Big Bang. So you can regard what we do as being like a sort of super microscope. But I would argue that those experiments also can give us insights into what happened in the very early phases of the universe, very close to the Big Bang. So in some sense, our machines are not just super microscopes, but also super telescopes. So here is a picture which illustrates for you some of the key phases in the early evolution of the universe. So some 380,000 years after the Big Bang, that's when atoms were formed. Before then, the universe was so hot and dense that there were no atoms, nuclei were ionized, and you had clouds of electrons, photons, and nuclei. So before then, no atoms, no chemistry, no biology. If you go back to when the universe was younger than 3 minutes, there wouldn't have been any nuclei either, because the pressure, the temperature would have been so high that nuclei would be dissociated. If you go back when the universe was less than a microsecond old, even protons and neutrons didn't exist. And if you go back when the universe was less than a picosecond old, so a millionth of a second after the Big Bang, we think that before then, particles didn't have any mass. And before that, there was a bang. So I've mentioned briefly dark matter. I'll be coming back to at least some theories of dark matter later on. According to many of those theories, dark matter would have been released something like between a picosecond and a microsecond after the Big Bang. And that's something which, in principle, we'd explore with our laboratory experiments. And we think that maybe at the same time as the masses of particles appeared, maybe around that time also, matter itself originated. So I've talked a lot about the connection between particle physics, astrophysics, and cosmology. It's perhaps worth remembering that much of particle physics actually started off at the beginning of the 20th century by observations of cosmic rays. So here's Victor Hess. He went up under a balloon. He discovered that the Earth was being bombarded by energetic particles, cosmic rays, and when they hit the atmosphere, their energy was converted into other types of particles, which scientists were then able to study. However, it was very difficult to make quantitative conclusions because we didn't know what particles were hitting the atmosphere, when they were going to arrive, from what direction, what energies, and so on. And so that's one of the reasons why, around the middle of the last century, particle physicists decided to take matters into their own hands and make their own particle collisions with particle accelerators, particle colliders in the laboratory. So that started in the 1950s, and in the 1960s, theorists suggested that these particles could be described by something that we call the Standard Model. So it's a somewhat prosaic term. If you've got a better idea, please propose it. But this standard model was proposed in 1967 by Abdus Salam, whom you see here, originally from Pakistan, together to American theorists Glashow and Weinberg. And their theory makes essential use of the ideas of Peter Higgs and the Higgs boson that I'll be returning to later on. So those ideas were proposed in the 1960s. People didn't really pay a lot of attention until the 1970s, when the first experiments started finding evidence for phenomena predicted by their apparently crazy theory. And if you come and visit CERN, just outside my office, you can see this piece of apparatus where the first key experiment was done. Later on in the 1980s, 1990s, much more detailed measurements were done. Those of you with good eyesight can perhaps see a tiny little red dot under the 3 there. So that's an experimental measurement, and the green line is a theoretical prediction. They agree this standard model works incredibly well. So, what does the standard model contain? Well, it's a theory of matter, so it contains particles of matter. I already mentioned the electron. I mentioned quarks. For some reason that we don't understand, there are 2 heavier particles, much like the electron, but heavier. And there's also neutrinos, very light particles that I don't think I'm going to have time to discuss in this talk. And then between these fundamental particles of matter, we distinguish 4 fundamental interactions. So 2 of these are very familiar to you. There's gravity, described by Einstein's general relativity that you heard about this morning. There's electromagnetism, a theory of light, radio waves, and so on, which was put together by James Clerk Maxwell in the 1860s. And then inside the world of elementary particles, there's a strong nuclear force that holds nuclei together and a weak nuclear force that's responsible for forms of radioactivity. So I like to think of these particles, these forces, as in some sense constituting the cosmic DNA. Their properties encode all the information you need to make all the visible stuff in the universe, including Donald Trump. It doesn't tell you why, but it tells you how. Well, there's one thing that's missing. So on this slide, there is no explanation for where particle masses come from, and hence there's no explanation of how it's possible for atoms to form. And that, of course, is where the Higgs comes in. And since I work for King's College London, I should mention that James Clerk Maxwell was professor at King's College London when he did his famous work. Okay, so let's talk about this problem of mass. So Newton, of course, told us that things weigh proportional to their mass. W equals mg. Einstein told us that energy is related to mass. E is equal to mc squared. But neither of them explained where the masses come from in the first place, and that's where this gentleman comes in, Mr. Higgs, and there's his theory on the blackboard behind him. So people have been asking me, where's my T-shirt? Am I going to reveal my T-shirt? The answer is, my T-shirt is here, and yes, I am going to reveal my T-shirt. So this formula which you see here describes all the visible stuff in the universe. So the first line describes the fundamental forces, think Maxwell's equations. The second line, how those forces act upon matter particles. The third line, how particles get their masses, according to Mr. Higgs. And the bottom line, well, that is the sort of engine room of the theory that makes the Higgs idea work. There will not be an exam on the theory at the end of the talk. According to this theory, there should be some new particle associated with this symbol phi, which I have here in the third line of the T-shirt, and that is the Higgs boson, which CERN found in 2012. And before I forget, Peter Higgs was an undergraduate student at King's College London. Just saying. So I'm not going to go into the details of the theory. I want to give you some idea of how the theory works. So the idea is that you should think that there is some universal field, as we call it, extending throughout space. And, well, maybe I could have got a better analogy here in Saudi Arabia. But think of a snowfield. Imagine that you're in Siberia in the middle of winter, and imagine that you're a particle trying to get through this Higgs snowfield, which extends throughout all space. So if you're lucky, you may have skis. In that case, you skim across the top of the snow. You don't sink down into it. You travel very fast. That's like a particle that does not interact with the universal Higgs field and travels at the speed of light because it has no mass, like the photon. Or maybe you've got snowshoes. So then you sink into the snow, you interact with the Higgs snow field, you go slower than the skier. That's like a particle with mass, maybe an electron. And of course, finally, you may be crazy enough to try to cross Siberia in boots. In that case, you're going to sink deeply into the snow. You're going to go very slowly. That's like a particle with a very large mass that interacts strongly with the Higgs field. Okay, that's the basic idea. A universal medium, and as you go through it, depending on how strongly you interact with it, you acquire a mass. But what is snow made of? What is the quantum of the snow field? It's the snowflake. And you can imagine that the Higgs boson is analogously the quantum, the basic unit of this Higgs field. So, of course, there's many, many different types of snowflake, right? Depending on how the molecules are arranged. And in fact, we physicists are still having a big argument as to whether there's something going on inside the Higgs boson that you can rearrange in different ways to make many different types of Higgs-like particles. But we don't know yet. Okay, so Peter Higgs proposed this idea back in 1964. Here he is working on some details of his theory in 1965. And much of particle physics now is concerned with what this Higgs particle may be telling us and what there might be above and beyond it. So I should declare my personal interest in this. I started working on the Higgs boson in 1975. At that time, these ideas were regarded as being extremely speculative and not very respectable. And so all the distinguished grey-haired professors in the front row would shake their heads. And that's why in our paper, where we did the first systematic study of the Higgs boson, we wrote, "We do not want to encourage big experimental searches for the Higgs boson." Fortunately, our advice was not taken. And the Large Hadron Collider was built at CERN, not just to look for the Higgs boson, but also to answer others of Gauguin's questions. So large, yeah, it's large. It's 27 kilometers in circumference. That's the Geneva airport on the right-hand side. Hadrons, that's our jargon term for protons and related particles. Collider collides those particles. So that's what it says on the tin. If you look inside the tin, this is what you see. So this is a picture taken inside the tunnel, about 100 meters underground. So that's a chain of magnets curving away into the distance. And through those magnets pass, when it's operating, thousands of billions of protons. Each of them has approximately the energy of a fly. They travel very close to the speed of light, and when the machine is operating, they produce billions of collisions per second. And in those collisions, we try to figure out, well, the origin of mass, the nature of the dark matter that I mentioned earlier on. We study the primordial plasma that filled the universe when it was a fraction of a second old, and we study the small difference that exists between matter and antimatter. So we make collisions, and around each of the collision points, there's a big piece of apparatus to detect the products of those collisions. So top right and bottom left, we have the two biggest detectors, ATLAS and CMS, which are the ones that co-discovered the Higgs boson and are now looking for dark matter. Top left, we have an experiment which is dedicated to understanding the properties of the cosmic primordial plasma. And bottom right, we have a detector looking for the matter-antimatter difference. And I'd just like to mention that there are some Saudi Arabian physicists who've been involved in these experiments, in particular in the CMS experiment there. So one thing I'd like to emphasize is that although these experiments are done at CERN, they're not done just by CERN. In fact, they're done by international teams of thousands of physicists with over 100 nationalities from all over the world, including, as I already mentioned, Saudi Arabia. So, what happened in 2012? The Higgs boson was discovered, and the way that I characterize the reaction in the particle physics community was to describe it as mass Higgsteria, when finally, 48 years after this particle was proposed, it was discovered. So how do you know that you made a Higgs boson? What does the Higgs boson look like? Well, actually, it doesn't look like anything because it's neutral. You can't see it directly. It decays very quickly. And the best that you can hope for is to look at what it decays into. And this is a computer simulation of a collision between two protons. So coming from top right and bottom left, produce dozens of charged particles, neutral particles indicated by those blue blobs, and two very energetic particles heading off to the right, and two more energetic particles heading off to the left. So that's what a Higgs boson might decay into. And if you go to the library, you can create your very own proton collisions. And if you kick hard enough, then you'll make events that look just like that. So what happened in 2012 was that ATLAS was able to start seeing those high-energy collisions. And so this is a computer reconstruction of the ATLAS apparatus. So you see a bunch of curved yellow lines there. Those are not very energetic particles that we're not very interested in. And you can see four almost straight red lines. Those are energetic particles that might have come from the decay of a Higgs boson, just like on the previous slide. So another experiment, CMS, also observed evidence for the Higgs boson. And this is a picture of their apparatus with a different type of event, where instead of four charged particles, we're looking at two very energetic neutral particles, probably particles of light, probably photons, one going bottom right and one going top left, and a whole bunch of other junk. So that was actually particularly pleasing to us because that was a process that we calculated back in 1975. So the experiment started seeing events of the type that one would expect from decay of a Higgs boson, but you have to see enough statistically to convince yourself that you really are seeing something new and not just a statistical fluctuation of other stuff. And that's what happened on July the 4th, 2012. Atlas and CMS convinced themselves that they really had seen a significant excess of events corresponding to a new particle. And that day, July the 4th, became known as Higgs Dependence Day. So here you see a bunch of happy physicists, and in the front you see a bunch of happy directors of CERN, and the one with his back to us, that's Lynn Evans, the guy who actually built the Large Hadron Collider accelerator, so he deserves probably more credit than anybody else for this discovery. So we were very fortunate on that day to have Peter Higgs with us on the right-hand side. And then the other guy is Francois Englert, who also proposed similar ideas, although he didn't mention explicitly the existence of this new particle. So, would you believe it? They proposed their theory in 1964. This is 2012, 48 years later, and in all that time, they had never met. This was the moment when they met in the CERN auditorium. So this is one reason why I like this picture. The other reason is because it shows you Fabiola Gianotti, who announced the discovery for the Atlas collaboration on that day, and has now gone on to become the Director General of CERN. So, no glass ceiling at CERN. Now, actually what happened on that day was that these experiments announced the discovery of a new particle, but we couldn't be sure straight away that it really was the Higgs boson that we've been looking for. It might have been an imposter. And I compare the situation to working on a jigsaw puzzle. So we particle physicists have been working on the particle jigsaw since 1897, and eventually we find something in the back of the sofa, a bent piece of cardboard, pictures rubbed off. Is this really the right size and shape to be the missing piece, to be the Higgs boson? So this is something which I studied a few years ago with my then student, Tivong Yu. And so the idea that we had was that the Higgs boson is supposed to give masses to other particles. So its couplings to its affinities with other particles should be proportional to their masses. So that prediction is the red line on this graph. What do the data say? The data, indicated by those little error bars, give you the dashed line with the uncertainty given by the dotted lines. Bang on. The couplings of this particle are totally consistent with the properties of the Higgs boson, and that's why we wrote in our paper that this particle walks and quacks like a Higgs boson. So our analysis was not very professional. Subsequently, the Atlas and CMS collaborations did a much better analysis with much better data, and they confirm that this particle does indeed couple to other particles proportional to their mass. So in 2013, the Nobel Prize Committee gave the Nobel Prize to Peter Higgs and Francois Englert, and they wrote in their citation, "Today we believe that, beyond any reasonable doubt, it is a Higgs boson." So my student and I were very proud because that quotation was taken directly from our paper. But what the Nobel Prize Committee didn't know was that when we sent our paper to the journal to be published, the journal said, "No, beyond any reasonable doubt is not a scientific statement." So in order to get our paper published, we had to remove the beyond any reasonable doubt. So not good enough for the journal, but good enough for the Nobel Prize Committee. So, discovery of the Higgs boson was a big deal. Without it, there'd be no atoms because electrons would run away from nuclei at the speed of light. There'd be no heavy nuclei to start off with. The weak interactions responsible for radioactivity would be much stronger. We would all glow in the dark. Life would be impossible. as I said, the discovery of the Higgs boson is a big deal. So is there anything else on the particle physics horizon? Should we expect any physics beyond the standard model? So here I take as my text James Bond, with one or two small modifications. And in particular, I paraphrase the title of the movie. The standard model is not enough. And in deference to James Bond, I give you 007 reasons for stating that. The first is that in the standard model, if you calculate the properties of empty space, you discover an instability, and we are doomed. So, to answer Gauguin's third question, what is going to happen in the future? The universe is going to collapse, if you believe the standard model. But probably you shouldn't. There should be physics beyond the standard model. And you need physics beyond the standard model to provide the dark matter that fills the universe. And you need physics beyond the standard model to explain the origin of matter. And you need physics beyond the standard model to explain the sizes of particle masses and the properties of neutrinos, and to explain why the universe is so big and old. And if you want eventually to make a quantum theory of gravity, which Priya was trailing during the course of her talk, again, you need physics beyond the standard model. So, you students out there, lots of things for you to work on. And experiments at the LHC are indeed studying many of these questions. So, let me just mention a few of them. Gauguin's third question. The future of the universe. Will it collapse? So here's a problem. So this picture here, the horizontal axis, is supposed to represent the amount of the Higgs field, or if you like, the depth of the Higgs snowfield. And we're sitting over here on the left-hand side with a not very thick layer of snow. However, there is another possible configuration over there on the right-hand side where the Higgs field will be ultra-dense. The snow field would be very, very thick. Now, at the level of classical physics, that's not a problem because there's a barrier in between the two. However, in quantum physics, everything fluctuates, and in particular, the value of the Higgs field fluctuates, and it could fluctuate through that barrier and take us from where we are now into that big crunch configuration where the enormous density of the Higgs field would cause the universe to collapse on itself. In fact, it's even more of a problem than that, because there's an issue of how we got to our current state in the first place. Because back in the early history of the universe, those fluctuations would have been much bigger, and most of the universe would have disappeared into that big crunch state. So we have to stop that, theoretically, and you have to make a wall, a big wall, which we can do with a theory called supersymmetry. So when people ask me, what's my favorite idea for physics beyond the standard model, I write supersymmetry in the most tremendous font that will fit on the slide. And I would argue that LHC has already given us several reasons for loving this theory. It would stabilize empty space. It made a successful prediction for the mass of the Higgs boson. It predicted correctly that the couplings of the Higgs boson would look like the standard model. And in addition, it does all sorts of wonderful things like help you make a quantum theory of gravity, help you unify all the particle interactions, and explain the dark matter. So in this talk, I'm not going to go into details into the theory of supersymmetry. I'll discuss those in more detail tomorrow morning. Suffice to say that according to that theory, all the known standard particles on the left have partner particles, written over there on the right with a twiddle on top, which, if it's true, would be a wonderful bonanza for future experiments at the LHC and elsewhere. Dark matter. So the hypothesis of dark matter goes back to the 1930s, and it was proposed in the form that we currently understand it by Fritz Zwicky, and it was based on observations of the Coma cluster of galaxies. So in this cluster, galaxies move around each other, but they move around too fast. You don't understand how gravity can hold them all together. The gravity generated by the visible stuff is not sufficient to keep them in place. So Fritz suggested that there's a stronger gravitational field which is generated by additional invisible dark matter. That's a somewhat Trumpian gesture, don't you find? I'm told that Fritz Zwicky has a rather special character. So that was the 1930s. 1970s, there were some observations, in particular by Vera Rubin, astronomer whom you see here, who I think was the one who really convinced a large fraction of the community that this dark matter hypothesis should be taken seriously. Because what she did was that she observed the motions of stars inside galaxies and found that they also orbit too quickly. In order to hold the stars in the galaxies, you needed additional gravitational field beyond that generated by the visible matter, dark matter. So what she observed, the motions of these stars in galaxies, are things that we call rotation curves, how fast something goes around the center of the galaxy. But let me give you a prototype of a rotation curve, the solar system. So you can measure the velocities of the planets as they go around the sun. They obey Kepler's laws. The further the planet is from the sun, the slower it moves. That's because the gravitational field gets weaker. But if you look at a galaxy, that's not what you see. Typically, if you look at a galaxy, so this is one example over here on the right-hand side. So the visible part of the galaxy is that little smudgy bit, the center. But you measure the velocities of stuff going around that galaxy, as is shown by those little points with error bars, and they keep going flat at more or less the same velocity out to very large radii. And as you can see, the stars, the stellar disk, and the gas that we know exists in the galaxy are not sufficient to explain that rotation curve. You need something additional, the so-called halo of dark matter. So there's many other reasons for thinking that dark matter must exist. For example, the structures that we see in the universe, the galaxies and the clusters of galaxies themselves, we believe formed by dark matter amplifying the very small fluctuations in density that existed in the very young universe. So what the astronomers tell us is that in addition to the visible matter, which is made up out of things like baryons and neutrons and so on and so forth, there is something like 29% cold dark matter and another 67% or so of so-called dark energy, which I probably won't have time to discuss, but I'd be happy to answer questions if you have them. So this I like to call the cosmic pizza. So you call up Domino's just over the road, and you ask for a pizza which contains 4% ordinary matter, 0.1% neutrinos, 29% of cold dark matter, and 67% of dark energy. and dominoes will think you're crazy, but that's what the observations of astronomy and cosmology tell us. So what is this dark matter? So many of us think that it's made of some sort of unknown particle, and in particular, it could be made out of those supersymmetric particles that I introduced a few minutes ago. So how would you know that these dark matter particles exist? The astronomers can't tell you. All that they can tell you about is the gravitational force generated by this dark matter. But we're interested in other interactions, in particular, interactions between this dark matter and standard model particles, presumably with some sort of new physics, not just gravitation. So we think that back in the early universe, when it was, let's say, somewhere around a picosecond old, that there would have been lots of dark matter particles in the universe, but as it expanded, they would have annihilated, disappeared into standard model particles. And what we can do at particle colliders is we can reverse that process. We can collide standard model particles and hopefully produce pairs of dark matter particles. Alternatively, we could look at the picture from the bottom and we could look for direct scattering of dark matter particles on standard model particles in some laboratory experiment. And it's also possible that there's still annihilations going on in outer space today, which maybe would contribute to the cosmic rays. Okay, so at the LHC, what we do is we start from the right, we collide standard model particles, and we try to produce dark matter particles. So this is the sort of thing that we are looking for. So this is a cross-section view through an LHC experiment. And what you can see is a bunch of stuff coming out. How energetic it is measured by the heights of those towers and those lines. Now, we can't see the dark matter particle directly because it only interacts very weakly, doesn't have an electric charge, doesn't interact with your detector, but it does carry energy and momentum. So we're looking for events where there is missing energy, missing momentum, invisible, carried away by dark matter particles, as in that simulation on the right-hand side. So you can see lots of stuff going down to the bottom right-hand quadrant, but nothing very much going in the opposite quadrant. In this simulation, that's where the dark matter particles went. So the experiments have been looking for events like that. They see events like that. Unfortunately, all the events that they've seen so far could be understood by standard model processes. No evidence yet for dark matter. And then you could try to look directly for the scattering of dark matter particles on regular particles in a deep underground laboratory. You go deep underground in order to reduce the radioactivity background coming from cosmic rays and so on. And what you look for is that when these dark matter particles go through, it deposits a very small amount of energy on a nucleus, which then you can hope to pick up by its thermal effects or by ultraviolet light and so on. So there's many experiments on this around the world. So far also, no results. So the search for dark matter continues. So these guys are not boldly looking for dark matter. What they did do was trigger the general interest in antimatter physics, which was further stimulated by this guy. So we physicists are also interested in antimatter, but not to blow up the Vatican or to power up Star Trek. What we're interested in is the very small difference between the properties of matter and antimatter that have been seen in the laboratory and the possible connection that might have with the fact that the universe as a whole contains blobs of matter, like in this room, but no large blobs of antimatter. So a little bit about the history of antimatter. So this was proposed in the 1920s by Dirac. So he was combining special relativity of Einstein with quantum mechanics, and he predicted that in parallel to the known particles, there should be other particles with the exact same mass but opposite internal properties like electric charge. And bingo, a few years later, antimatter particles were discovered in the cosmic rays. In fact, now we use them routinely, not only to do experiments, but they're also used routinely in diagnosis using PET scanners. So, equal and opposite, Dirac said. Not so. Experiments discovered that the weak radioactivity interactions of matter and antimatter are slightly different. And we don't really understand why. But it's possible that that small difference between the matter and the antimatter might be connected with the fact that there's a big asymmetry in the universe between the amounts of matter and antimatter. And we hope that experiments at the LHC and elsewhere will help establish that connection. So this connection was actually proposed by the Russian physicist Sakharov back in 1967. And this is a picture of Sakharov. He's the guy with the glasses looking towards you. He came to CERN around the time of the collapse of the Soviet Union, and discussions with physicists, as you can see here. So he said, if you want to make the matter in the universe, well, first of all, you need interactions that create matter. So those are predicted by theory, although they haven't yet been seen by experiment. And you need some some change with time in the condition of the universe. For example, the expansion of the universe. And it's possible that during the expansion of the universe, the Higgs boson that I mentioned earlier on could play a role in helping to generate this asymmetry, this cosmological asymmetry between matter and antimatter. And as I mentioned, the experiments at CERN and elsewhere are looking into this possibility. We hope that we can establish some connection between the matter-antimatter symmetry that we see in the laboratory and the cosmological matter-antimatter symmetry. So finally, I'd like to come back to this guy. So you recognize him. He's a bit older than in my earlier picture, but you can recognize the eyes, right? And I think he looks a little bit sad. So it may be because he had some premonition that he was never going to be able to realize his dream of unifying all the fundamental interactions, including gravity. So he didn't succeed, but many of the ideas that he worked on are still being worked on by theoretical physicists today. In particular, one of the ideas that he played with was the possibility that there might be additional dimensions of space. I guess I should have proposed additional dimensions of time, but no, additional dimensions of space. And this is an idea that's become very popular in recent years, in particular with something which is called string theory, which you may have heard of. I think that's the best candidate we have for a theory to unify all the fundamental interactions and to make a quantum theory of gravity. Now, according to some of those theories with extra dimensions, it's possible that gravity might become a strong force at the energies of the collisions at the LHC. And in such a case, it's possible that the LHC experiments might create black holes. So here we are back at Priya's talk again. Now, Priya was talking about black holes which weigh minimum as much as the sun, maybe billions of times the mass of the sun. I'm not talking about that. I'm talking about microscopic black holes that weigh an infinitesimal fraction of a gram. So when the LHC was about to start up, some people got rather worried. We're going to make black holes, they're going to eat up the entire Earth. Of course not. They wouldn't have time to eat up anything because they would vanish instantly, they would decay, and they would disappear. And if you don't believe that argument, remember that Earth has been getting bombarded by cosmic rays for billions of years, and we're still here. So I don't think that cosmic ray collisions, or indeed LHC collisions, could produce anything dangerous. But if they produced microscopic black holes, that would be fascinating, because it would provide us with an experimental way of testing our ideas about quantum gravity. So we're looking very hard for microscopic black holes, but no luck so far. So that brings me to the end of my talk. I hope that I've convinced you that the CERN Large Hadron Collider is not only the world's most powerful microscope, looking deep inside the atom and telling us more about Gauguin's question, what are we? But it is also, in some sense, a super telescope capable of addressing Gauguin's other questions: where do we come from and where are we going? Shukran. So we have a Q&A now. Okay. While they're getting themselves organized over there, does anybody have any Qs? And I'll try to A.
Hi, Professor. Amazing talk. I have a question on the particle-wave duality. So, what you have just explained is can be explained with the particle being a particle, but we also know that it can also behave as a wave. So how does that gets incorporated in this theory?
Okay, so the particle-wave duality is a basic feature of quantum mechanics, and it underlies, for example, the equivalence between electromagnetic waves and the photon picture of light, which, by the way, was postulated by Einstein, and that's actually how he got his Nobel Prize. So you can regard the Higgs boson that I talked about as being very analogous to that. So electromagnetic wave, electromagnetic field, particle, photon. Higgs field, particle, Higgs boson. So in fact, the central theme of what I was saying was very much related to this idea of the wave-particle, the field-particle duality.
Yes, I have a question. How will you relate the LHC and the founding of the Higgs boson to lead to the discovery of the string theory? And what could be done other researches which could lead to 10-dimension and supersymmetry in the string theory? Thanks.
Right. So I mentioned one possible way of probing some versions of string theory, which is to look for theories with large extra dimensions via this sort of strong gravity effect through microscopic black holes. That's maybe too dramatic. But there are other things that you can look for. For example, when the particles come out, the rates can be calculated assuming that the particles are elementary points. But according to string theory, they're spread out. And so you can look to see whether there's a deviation from the predictions from the point-like calculations that we normally do. So people have done those experiments, and we know so far that the string scale must be, let's say, several dozen times the mass of the Higgs boson, to put it in simple units. But it could be very much, much, much larger than that. In which case, I think that experiments at the LHC are probably not the way to go, but we come back to astrophysics and cosmology. And so one idea that I've been proposing with some of my colleagues is that if you look at very, very energetic particles, which should travel at the speed of light, maybe they don't, because maybe as they go through space, they excite quantum effects in the space-time continuum, and they get slowed down and travel at less than the speed of light. So various experiments have looked for such an effect. Hasn't been found yet, but that's another possible alternative way for looking for some hint of quantum gravity and possibly string theory.
Hi, thank you for your talk. Quick question. Do we need a larger hadron collider?
Of course. Well, so we have this big open question about dark matter, and there's many other issues as well. So we certainly need to push our experiments further. So currently the LHC is undergoing an upgrade, which will increase the energy very slightly, but produce many more collisions. But I think in the long run, even if we discover something with that upgrade of the LHC, if we really want to understand things in any detail, we're going to need to produce much more particles and go to higher energies. And there's a big discussion taking place in the particle physics community around the world about what might be the next step. And so I was talking about the LHC, the Large Hadron Collider. So we plan to demote it to the Little Hadron Collider, and we would like to build a bigger tunnel, maybe 100 kilometers in circumference, which could get to much higher energies. But that is still at the proposal stage.
Thank you. I just want to ask a question. How could you say something, it is a discovery? Because, it's in the world of particle physics, we cannot see the thing. We cannot, we cannot see the experiment directly. So how could you say that, oh, this thing is a new particle, or this is a part of the particles, or this is something new? Are you, let's say, matching the experiment with the numerical simulation, or you are doing the numerical simulation, or maybe during the numerical simulation you see, oh, maybe this is something unique, or maybe there is an error in this different? I just want to know, how could you say something that it is a discovery in the particle physics? Thank you.
So we do calculations within our standard model, applying the laws of quantum mechanics, applying the laws of special relativity, which work extremely well. And we predict phenomena, and experiments, if we're lucky, find phenomena that agree with those predictions. And the theory that predicted those phenomena, that's far and away the most economical explanation for what we see. So I'm sure that there's philosophers of science and epistemologists out there who are going to say, you can't possibly claim that you've discovered something. But I think you can.
Look, I want to ask about the interactions with the Higgs field and why particles have mass. So we know that it's the interaction with the Higgs field that gives mass to the particles. So I want to ask about the chirality. For example, electrons, they have left-handedness and right-handedness, and one of these, they each interact differently with the Higgs field, and one is sort of affected more than the other. And could you explain why it has a preference for one and not the other? Where does this preference come from?
Okay, so in fact what the Higgs field does is that it couples one chirality to the other chirality. So its other interactions, in particular the weak interactions, work differently for particles of different chirality, or better said, particles of different helicity. But the Higgs couples the two together. So it's not that the Higgs couples to the left or it couples to the right. It actually couples the left to the right.
Okay, thank you for your talk. I want to ask about the difference between ether and field.
Between
the ether.
Ether,
and field.
yeah.
So, what is the difference between these?
So the ether was a pre-relativistic concept, okay? And the idea was that there was some preferred reference frame, and that defined the ether for you. So in fact, of course, relativity came along and it said, well, there's no preferred reference frame. There is no ether. So Einstein proposed the special theory of relativity. I am told, without even being aware of the Michelson-Morley experiment, that had failed to find the ether. Now, perhaps what you have in the back of your mind is this Higgs field, this snow that I'm talking about, that sounds a lot like the ether. And the way that I presented it, maybe it sounds too much like the ether, because, of course, a snow field does have a preferred reference frame, just like the old ether did. But the Higgs idea is a completely relativistic concept, and it does not have a preferred reference frame, and so it's very different from the classical idea of the ether.
So my question is the following. As far as I know, the particles predicted by supersymmetric theories are within the energy range of the LHC, but still no supersymmetric particle is observed today. So where does your hope for supersymmetry come from?
Okay, so I can interpret your question in a couple of different ways. So it could be that the supersymmetric particles are just a little bit heavier than what we were originally thinking, and we just have to make a few more collisions and we'll find them. I certainly hope for that scenario, because then I might actually get to see supersymmetric particles in my lifetime. But when you're asking why do I hope to see supersymmetry, that's because I love the theory of supersymmetry. It's a very elegant, it's a very powerful theory that could explain at the same time many different phenomena. And I think it would be a real shame if nature didn't use it.
So I think we're going to allow for one more question, please.
Okay. Thank you very much for a fantastic talk. You mentioned philosophers and epistemologists, and I'd like to ask a question along those lines, possibly. So if you talk to philosophers, they'll say that science can't explain what happened before the Big Bang, as the scientific laws were created with the Big Bang itself. And my question to you as the scientist is can science possibly advance enough to tell us what happened before the Big Bang?
Okay. So the laws that we have established so far, and the laws which I think we can reasonably hope to establish in the foreseeable future, tell us what are the laws that govern the behavior of the universe after the Big Bang. But if we try to extrapolate back to time equal to zero, we can't, because the equations encounter a singularity, much like the singularity that was mentioned in this morning's talk by Priya. So we can't get to t equal to zero with our current approach to physics. And a fortiori, I would claim that we can't talk about time less than zero. We don't even know whether time less than zero existed or not. It may well be that there was no t equal to zero at all, that time just didn't exist. It may be that time is just an emergent phenomena that started up after the Big Bang, but not at or before the Big Bang. And I guess that's my favored point of view. And when people start presenting theories about what happened before the Big Bang, I tend to check my email. Anyway, so we got back to time at the end of the talk.
On that note, I want to thank Professor John Ellis for an for a really great talk. It was an open-minded talk. And I would like to remind you that we do have the chance to continue this conversation, this discussion tomorrow between 11 and 12. Thank you very much, Professor.
So, John,